Sorry about being a little late to the Zoom meeting. So the chapter 22 homework is due on the 11th. The chapter 23 part 1 homework will be due on the 18th. Part 2 will be due on the 25th. So we were talking about Faraday's law. So Faraday's law of induction says that the EMF induced is minus N. Let me change this to minus N, the number of loops in a loop, times the change in flux over the change in time. And that flux can change by either the field going through the loop changing or the loop entering or exiting a field, or lastly, the size and shape of the loop changing. Lenz's law is about the direction of the induced EMF. And it's that an induced current will also always flow in a direction that opposes the change that caused it. So if the magnetic field is increasing, the magnetic field created by the induced current will be in the opposite direction. If decreasing, it will be in the same direction. That means if you point your thumb in the direction, your right thumb in the direction of the flux, if that flux is increasing, it will be opposed, so it will be opposite. It will, your fingers will curl in the direction opposite. So if you point your thumb in the direction of the flux, if the flux is decreasing, the direction your fingers curl will be the direction of the induced current, and it will be opposite if the flux is increasing. Basically, think about what the current that is being created would, what magnetic field it would create, and then make sure it points in the direction that would oppose the change that is occurring. And here's how we can actually calculate the induced EMF, derive the Faraday's induction law. Well, no, calculate the induced EMF and work. So here we're going to calculate the induced EMF and figure out sort of the work it's doing. And this will tell us about what kind of thing will be induced in a bar moving through a magnetic field. So we can think about mechanical work and electrical energy. Tie them together. So, given a resistor and the thing, if you apply some external force that will be to oppose the magnetic force that will be created by the current flowing, as you increase this area, because you're moving this to the right with some speed v, you increase the area as you move this bar through a magnetic field at some speed v. So v times delta t gives you this change in area. And that's the length of the bar times v times delta t. So this area times the magnetic flux times the magnetic field gives you the change in flux. So that is v delta t times length. The change in flux is b v l delta t. The induced EMF is the number of turns, which is 1 BVL delta T over delta T, which just gives you BVL. So if you move a rod through an electric field, through a magnetic field, it induces an EMF equal to BVL. And this creates an electric field in the rod equal to B times the velocity of the rod. Because voltage is the delta T's cancel, we get BVL. And the electric field is the derivative of the voltage, so it's BV. And if the rod is going to move at a constant speed, some external force needs to be exerted on it. This should have equal and opposite magnitude to the direct magnetic force. So that force will be current times length times magnetic field. Current is the EMF over the resistance, so BVL over resistance, because V equals IR, times the length, so B squared VL squared over R is the force required to move that rod connected to a circuit through an electric field. This is generating a current by moving from mechanical energy. The mechanical power is force times velocity. So B squared VL squared over R, which is B squared V squared L squared over R. The electrical power in the light bulb is I squared R. Well, I is BVL R over R squared, which is B squared V squared L squared over R. So mechanical power is converted directly into electrical power. This shows you that mechanical power converts directly into electrical power. And so you could also do it with V squared over R, which is just BVL over R, BVL squared over R. So here we have a rod that moves through a 0.31 Tesla magnetic field and experiences an induced electric field of 0.899 volts per meter. So how fast is the rod moving? So we showed that a rod moving through an electric field has an induced voltage between the ends of BV times the length of the rod, and an electric field induced in it of B times V. So I'll let you work on this for a few minutes. So we know the electric field is magnetic field times velocity if you're moving perpendicular to the magnetic field as you are here. The velocity is just going to be the electric field divided by the magnetic field. So 8.99 volts per meter divided by 0.321 Tesla gives you 2.77 meters per second. Here we have a light bulb with a resistance of 22 ohms, and it consumes 5 watts of power. The rod is 1.25 meters long and is moving to the left with a constant speed of 3.1 meters per second. So what is the strength of the magnetic field? And what external force is required to maintain this rod's constant speed? So remember that the voltage is magnetic field times velocity times length. And because of that, power is magnetic field squared times velocity squared times length squared divided by resistance. And the force is just power divided by velocity. So magnetic field times velocity times length squared over resistance. So I'll give you a minute or two to work on this. Okay. So for part A, what's the strength of the magnetic field? Well, we know the power is the magnetic field squared times the velocity squared times the length squared over the resistance. And then we can solve that for magnetic field. Magnetic field squared is power times resistance over velocity squared times length squared. The power is 5 watts. The resistance is 22 ohms. The velocity is 3.1 meters per second, and the length is 1.25 meters. So if we take the square root of both sides, magnetic field is square root of power times resistance over velocity times length. So square root of 5 watts times 22 ohms over 3.1 meters per second times 1.25 meters, which comes out to 2.7 Tesla. That's part A. Part B, what external force is required to maintain this rod's constant speed? Well, power is force times velocity, so velocity is power over speed. So force is power over velocity. 5 watts divided by 3.1 meters per second gives you 1.6 newtons. Here we have the same setup. The light bulb in the circuit has a resistance of 22 ohms. Consumes 5 watts of power. The rod is 1.25 meters long, and it moves to the left with a constant speed of 3.1 meters per second. So what's the work done by the external force in 0.58 seconds? And the energy consumed by the light bulb in the same amount of time? So this is fairly straightforward. The work done by the external force is just going to be equal to the power consumed by the light bulb times the time it takes. So power is work times time. Work is power times time. So the work that's being done by this is 5 watts times 0.58 seconds. So both of these, A and B, will be 2.9 joules. So the work done by the external force will equal the energy of the light bulb, which equals 2.9 joules. So what would happen if we double the length of the rod? By what factor does the magnitude of the external force change? And by what factor does the electrical power change? I'll let you think about that for a couple of minutes. So this is something where we just need to look at the equations for this. So if we think about this, let's think about what factor the external force will change by. Well, our initial force is B squared V L squared over R. And if we double the length, nothing else changes. We'll end up with 4 times our initial force. Because B squared V becomes B squared V times 2L squared. The 2 gets squared, you get 4. The 4 comes out, and that's 4 times force 1. And we can do a similar process with the power, which is B squared V squared L squared over R. And we will also end up with 4 times the power. So now we've talked about how mechanically moving a object through a magnetic field creates an electrical current. Well, an electrical generator is a device that converts mechanical energy into electric energy. So you use some sort of outside source of energy to rotate a coil, thereby generating electricity. This is sort of the simplest ideal electric generator, one coil in a simple magnetic field, a couple of slip rings. This will generate an AC current. Actual real generators use multiple coils and more complicated alternating magnetic field shapes, just because you can get more power out, passing more loops through more changes in magnetic fields that way. Basically, you get faster oscillate. Yeah, you get effectively bigger changes then. The induced EMF of a rotating coil will vary sinusoidally, like this. And that EMF is going to be the number of turns times the magnetic field times the area of the loop times omega times sine omega t, where omega is the angular velocity of the rotation of the coil. And an electric motor is the opposite. It uses the torque on a current loop to create mechanical energy. And again, this is sort of the idealized, simplified version of an electric motor. Real electric motors are different. Again, they have multiple coils. This is an AC motor, again, a simple one. Real AC motors actually use multiple coils that create the magnetic field as well as are turned by it, but as a general idea. So here, if the coil in an electric generator, remember the EMF or voltage of an electric generator is the number of turns, and this is the magnetic field, times the area times omega, where omega is 2 pi times the frequency, because it's the angular velocity of the rotation. So the coil of an electric generator has 125 turns and an area of 2.42 times 10 to the minus 3 square meters. And it's desired that the maximum EMF of the coil be 169 volts when it rotates at a rate of 60 cycles per second. So the maximum is going to be when the sine is 1. So N times B times A times omega. So what's the angular speed of this generator? And then what's the strength of the magnetic field B that's required for this generator to operate at the desired voltage? So an electric generator, we have 125 turns, an area of 2.42 times 10 to the minus 3 square meters. And we want an EMF of 169 volts when it rotates at a rate of 60 cycles per second. So the first question is, what's the angular speed of the generator? Well, the angular speed, omega, is just going to be 2 pi times the frequency. So 2 pi times 60 hertz, 377 radians per second. And EMF is going to be N times B times A omega times sine omega t. We want the maximum. That's just going to be when sine is 1. So NBA omega. So if we want to find the magnetic field, it's the maximum divided by NA omega. So 169 volts divided by 125 turns times 2.42 times 10 to the minus 3. Square meters times 377 inverse, seconds gives a magnetic field of 1.48 Tesla. So here we have this generator. So the question is the magnetic flux through the loop maximum when the plane of the loop is perpendicular to the magnetic field? And is the induced EMF produced by the loop maximum when the plane of the loop is perpendicular to the magnetic field? So remember, induced EMF is proportional to change in magnetic field. And sorry, change in magnetic flux. So what is the magnetic flux maximum? And then what is the maximum of the induced EMF? So I'll let you think about that. So if we think about part A, when is this going to have maximum magnetic flux? Well, the flux is BA cosine theta. It will be maximum when theta is 0, which is the point where the plane of the loop is perpendicular to the magnetic field. Because theta is measured from the perpendicular to the plane of the loop. Our reduced EMF is N d phi dt, which is d dt BA cosine, which is minus N d dt BA cosine theta. So N minus BA sine theta d theta dt. So NBA omega times sine theta. This will be maximum when theta is 90 degrees, which is the point when the loop is parallel to the magnetic field. It is minimum when it is perpendicular, because that's the point of minimum change. The maximum is at theta equals 90 degrees. So this is perpendicular, and this is parallel. In fact, I should put that in slides. Let me just see if I can insert. I'll type it in later. So now we're going to move on to inductance. So the thing is, when you have a coil with a current running through it, if you change that current, it's going to induce a magnetic field. You know, it will create a magnetic, well, if you have a coil with a current running through it, it creates a magnetic field. If you change that current, it will induce an EMF, because a change in current will induce an EMF to oppose it. And this is inductance. So here, if you close the switch on this circuit, a current is established, and it will increase with time. You'll have an increasing magnetic field in the coil. So that will create a current that opposes that increase. So inductance is a proportionality constant that tells us how much EMF will be induced for a given range of change in current. So capacitance is proportional to charge. So how much charge is built up? So the integral of current. Inductance is proportional to the rate of change of current. So the derivative of current. So the definition of inductance, there's a voltage induced that is equal to the number of turns times the change in flux over time, which is equal, we define inductance to be, inductance is a proportionality constant, which converts from EMF to be equal to the change in current over time. So if we solve for L is equal to N over d flux over di. No. The EMF induced is equal to the inductance times the change in current over time. The unit of inductance is volt seconds per amp. Which is a Henry. So the unit of inductance is the Henry. And if we solve for L, N is equal to the change in flux over the change in current. So given the definition of inductance, you can calculate the inductance of a solenoid. It's the change in flux over the change in current. We have a formula for the magnetic field in a solenoid. Now let me write this out. Because the magnetic field is mu naught N over L oops, I have the wrong controls. Mu naught N over L times I, so flux is mu naught N over L times I times cross-sectional area. So L, which is N times delta flux over delta I, ends up being mu naught N squared over L just times area. And when used in a circuit, such as a solenoid, such a solenoid or other coil is called an inductor. So here we have a coil and an electromagnet that carries a constant direct current of 3.9 amps. When a switch is suddenly opened, the current drops to 0 over a time of 2.5 times 10 to the minus 3 seconds, or 2.5 milliseconds. If the magnitude of the average induced EMF during this time is 8.1 volts, what is the inductance of the coil? Remember, inductance is induced EMF is inductance times di dt, the rate of change of current. We'll give you a couple of minutes to work this out. So, EMF is inductance times di dt. So, inductance is going to be EMF times delta t over delta I. So 8.1 volts times 2.5 times 10 to the minus 3 seconds divided by 3.9 amps, which gives 0.00519 henries, or 5.19 millihenries. So here we have a 500 turn solenoid that is 8 centimeters long. When the current is increased, oops, that's a typo, from 0 to 2.5 amps in 0.35 seconds, the magnitude of the induced EMF is 0.012 volts. Find the inductance and the cross-sectional area of the solenoid. quickly fix that typo. So for this, we have 8 centimeter long solenoid. When the current in the solenoid is increased from 0 to 2.5 amps in 0.35 seconds, the magnitude of the induced EMF is 0.012 volts. So we want to find the inductance and the cross-sectional area. Well, the inductance we can figure out from the change in current, the time, and the induced EMF. So the inductance is going to be, EMF times delta T over delta I, 0.012 volts times 0.35 seconds over 2.5 amps. The inductance is 0.00168 henries or 1.68 millihenries. The inductance is also going to be mu naught times the number of turns squared over the length times the area. So we're going to divide by this, divide the inductance by this. We get area equals inductance times length over mu naught times n squared. And we can plug in these numbers. 0.00168 henries times 0.08 meters, that's 8 centimeters, divided by 4 pi times 10 to the minus 7 henries per meter, that's mu naught, times 500 turns squared, which gives us a cross-sectional area of 0.000428 square meters, or 4.28 square centimeters. if I did that unit conversion correctly. So here, the inductance of a solenoid that is 5 centimeters long is 0.157 millihenries. If its cross-sectional area is 1 times 10 to the minus 4th meters squared, how many turns does the solenoid have? So remember, the inductance of a solenoid is mu naught times n squared over L times the cross-sectional area. So inductance equals mu naught n squared over L times A. We know inductance, mu naught, length, and area. We just need to solve for n. So n squared equals length, inductance times length over mu naught times area. So n is just going to be the square root of that. So that's the square root of 0.00157 henries times 0.05 meters, that's 5 centimeters, divided by 4 pi times 10 to the minus 7 henries per meter times 1 times 10 to the minus 4 square meters. Comes out to 6.246 times 10 to the 4. And the square root of that is around 250 turns. And that is all I wanted to cover for today. I will see you guys on Thursday. Have a nice day. Oh, and your midterm grades are up. So you can check them. You all did pretty well. I'll stop sharing and I'm going to end the meeting.